Welcome back to another video about eigenvalues and eigenvectors, and we're going to go a little deeper into the idea here using this new example matrix here, 4, 1, 3, 6. We want to do three things here. First of all, show that lambda equals 3 is an eigenvalue for this matrix, and then find an eigenvector that corresponds to it. Then we'll do the exact same thing for lambda equals 7, and then we're also going to show that lambda equals 2 is not an eigenvalue for this matrix. So after this video is over, you're going to be able to do two very important things regarding eigenvalues and eigenvectors. If you're given a number and a matrix, you'll be able to tell whether that number is or is not an eigenvalue for the matrix. And if it happens to be an eigenvalue for that matrix, you'll be able to go and find an eigenvector that goes with that eigenvalue. So let's dive in. So let's start by rewriting the matrix that we're dealing with here, and that is A equals 4, 1, 3, 6. And we're going to show that lambda equals 3 is an eigenvalue for that matrix. Now let's just recall the definition, and what does this mean? That should mean that there exists a non-zero vector x, such that a times x is equal to 3x. That's what it would mean for lambda equals 3 to be an eigenvalue for this matrix. And that non-zero x, it would be an eigenvector that corresponds to lambda equals 3. So we're going to show that there exists a non-zero solution to this equation, in other words. Now focusing in on that equation is really important. Let's go over here to the left and start working with it. Let's copy it down first of all. Ax equals 3x. Now I'd like to see if there are non-zero solutions to this equation. And how do I do that? Well, let's just start trying to solve it. A typical algebra step would be to subtract 3x from both sides. Now this is a vector that I'm subtracting, and so on the right hand side that wouldn't be the number 0, it would be the 0 vector. I'm going to do one thing here on the left hand side that will make things easier in a moment, and that is, instead of writing 3 times x, I'm going to write 3 times the identity matrix times x. Now the identity matrix times x is just x itself, so nothing really changed here. What this is going to allow me to do is, you see the common factor of the vector x on here on the left, I can now remove it. And then as what's inside makes sense, this is going to be a 2 by 2 matrix, A minus 3I here on the inside. Now just to touch base, what we're trying to do is find non-zero solutions to an equation. We started with this equation over here, but now we're here to this equation. So I just want to point out that what we're looking at here is not just any kind of equation. This is a homogeneous equation. Homogeneous. The right-hand side of the equal sign has the 0 vector in it. So you know what we're doing here is something we've been doing for a long time in our class, and that is finding non-trivial, non-zero solutions to a homogeneous equation. So I think we have a shot at actually answering this question. What's going to be important for us now is to drill down into what is this matrix right here, A minus 3I. So let's just write it out. Well, A, as you know, is the matrix 4, 1, 3, 6. And the identity matrix would be 1, 0, 0, 1. 3I is 3, 0, 0, 3. So let's just perform the subtraction step and see where we're at. I'm going to have 1, 1, 3, 3 when I'm done. And so let's just feed that back into here and pull the whole mess of it up to right there. And let's see what we got. I'm now looking at the following system. 1, 1, 3, 3 times the vector x equals the 0 vector. It's a homogeneous equation, and I'm asking, do there exist non-trivial solutions? And the answer is, oh yes there are, because look at the columns of this matrix. The columns of that matrix are not only linearly dependent, they're actually equal to each other. And so there will be non-trivial solutions to this equation. So non-trivial solutions exist. Non-trivial solutions do exist to this, and so what that tells me is that lambda equals 3 is indeed an eigenvalue. Okay, so But that's only part of what we were trying to do. We were also trying to come up with an eigenvector that corresponds to this eigenvalue. What is that eigenvector going to be? Well, it will be any of these non-trivial solutions. If I can find a non-trivial solution to this equation, remember that's the same thing as this equation when you get down to it. And so any non-zero x that solves this equation will be an eigenvector corresponding to lambda equals 3. So what we should do now is go through and get the general solution for this system. Let me just erase some of the stuff here to make some room. So let's get the general solution. This shouldn't be too bad. I'll write it in an augmented matrix form, 1 0 1 1 0 3 3 0. If I reduce this to row reduced echelon form, I have 1 1 0 0 0 0. That free variable tells me I've got a solution, which I already knew, and so the x2 is free, and it looks like the x1 is equal to negative x2. Okay, so one potential eigenvector that corresponds to lambda equals 3 would be, for example, 1 minus 1. Okay, or anything that's parallel to that. And we could check this just to make sure. If I take 1 minus 1 times a, let's see what I get. I would take 4 1 3 6 times 1 minus 1. Let's just see what we get. If this is really an eigenvector for lambda equals 3, what I'm supposed to come up with is 3 minus 3. Let's just see if we do. So I'd have 4 minus 1, that's a 3. Then I have 3 minus 6, that's minus 3. So that checks out. As we learned in the last video, any vector that is parallel to this, that lies on the same line as 3 minus 3, will also serve, or 1 minus 1, will also serve as an eigenvector for lambda equals 3. Now, if you understood that example, you don't need to follow the next example. You can skip on to the final one, but just in case you need a little bit more data, let's also show that lambda equals 7 is an eigenvalue for the same matrix. Let me copy it down, 4 1 3 6. And let's deal with lambda equals 7. So again, what I'm trying to show here is, or see, is if I have non-zero solutions, are there any non-zero solutions to the equation ax equals lambda x? In this case, lambda is 7. So let's set up that equation over here, ax equals 7x. And just do some basic algebra on this. Let me subtract the 7x from both sides, and I have ax minus 7x. Again, this is equal to the 0 vector. I can't subtract 7 from a, so I need to put in this identity matrix right here. And now let me pull out the factor of x here. So I have a minus 7i x equals the 0 vector. And now I'm asking myself, are there any non-zero solutions to this homogeneous equation? So that's where it became important to look at the coefficient matrix right here, a minus 7i. So this is 4, 1, 3, 6, minus, now 7 times the identity matrix is 7, 0, 0, 7. And let's just compute what that is. That is going to give me minus 3 minus 1, and 3 plus 1, no, minus 1. And this is supposed to be a plus up here. Okay, and so now let's feed that back into the system and rewrite it. I'm now looking for non-zero solutions to this system, which is minus 3, 1, 3 minus 1 times x equals the 0 vector. Now it's pretty clear that the columns of this matrix are linearly dependent. So I know that there are going to be non-zero solutions to the system. So that tells me that lambda equals 7 is an eigenvalue. Again, because I know that non-zero solutions exist to this homogeneous equation. And the reason I know that is because the columns of this matrix are linearly dependent. Now let's push it ahead a little bit farther and find an eigenvector that corresponds to that eigenvalue. And to do that, we're going to need to get the general solution for this system. So let's write out the augmented matrix, negative 3, 1, 3, minus 1, and I augment with 0, 0. That will pretty clearly row reduce to, in echelon form, 3, minus 1, 0, 0, 0, 0, and let's rescale that top row by a factor of a third to give me 1, negative 1/3, 0, 0, 0, 0. Okay, so here again, I've got a free variable in x2, and it looks like x1 in this case is going to be 1/3 x2. Okay, so I can just choose any non-zero value of x2 that I want here, and I'll get my eigenvalue. I think it'd be convenient to choose x2 equal to 3, and so one potential solution here is 3, and that would make the x1 coordinate 1. I don't have a lot of room here on this, but you can check that a times this is actually equal to 721. Now finally, what we haven't done yet is shown that a given number is not an eigenvalue for this matrix. So let's see how that works. So again, I'll just copy down 4, 1, 3, 6. And what we're going to do is show, we want to show that lambda equals 2 is not an eigenvalue for this matrix. So what would that mean? Well, that would mean that if I tried to look at the equation ax equals 2x, that would have no non-zero solutions. In other words, the only solution it would have is the zero vector. The zero vector is pretty clearly a solution to that equation. Just plug it in and you'll see. What we need to show is that there aren't any other solutions to that equation other than the zero vector. So this is going to look a lot like the first two examples, but with a bit of a twist here at the end. So let's write out the equation. Ax equals 2x. As usual, let me subtract the right-hand side from both sides to get this. And we know that this is equal to ax minus 2 identity matrix x equals 0. And let's pull out the x, and I have a minus 2I x equals the zero vector. Okay, again, I'm working with a homogeneous system here, and I need to know what this a minus 2I business is. So let's compute that right down here. So a, of course, is upstairs. That's 4, 1, 3, 6, and I'm subtracting off 2, 0, 0, 2, 2 times the identity matrix, and that, of course, is going to give me 2, 1, 3, 4. Okay, and that's what this green matrix is here. So let's pull this up and look at it some more. So the a minus 2I now is the matrix 2, 1, 3, 4 times x equals the zero vector. Now the question we're asking is, are there any non-zero solutions to this equation? And the answer here this time is that no, there are no non-zero solutions. That is, the only solution is the trivial solution. And how do I know that? Well, I can just look at these two columns here. Since there are only two of them, I can pretty plainly see that one's not a scalar multiple of the other. And so that makes these columns linearly independent. Okay? But the fact that those columns are linearly independent means that I have an invertible matrix right here. That's from the invertible matrix theorem. And if that's the case, then the only solution here is x equals 0. So lambda equals 2 is not an eigenvalue for this matrix. Is not an eigenvalue. So again, to recap, what we know how to do now is if I'm given a square matrix and I'm given a number, I know how to check whether or not that number is an eigenvalue. And I also know that if that number happens to be an eigenvalue, I can use a method similar to this, or in the first example, to go through and find an eigenvector that corresponds to it. The last remaining question, which is something we're not going to be able to pick up until a bit later, is where do you get these eigenvalues in the first place? Do we just try numbers until we succeed, or what? We don't know how to do that yet, but we will soon, so stay tuned.